we're going to go on and look at today's chapter 4.5, graphs of sine and cosine function, using periods and whatnot. We'll really not sketch too many of these because, one, the graphing calculator will do them, and that's really it, because there's other features that will sketch a lot of these here, and really just knowing kind of just the difference parts and being able to recognize what they are is going to be more important. In this section, now a sine function is represented by this here. And as we know that the y values are the values that come out of sine will not be greater than 1 or less than -1, just as the basic sine function. But it will repeat all the values in between, so we get this wave. It's going to repeat itself every 2 pi. It has a period of 2 pi because it repeats itself every 2 pi units. And we can move those 2 pi units, or those points, every 2 pi to get the same function, and it's going to repeat itself over that. And the cosine function, similar, it repeats itself every 2 pi, but if we notice sine starts at 0, cosine starts at 1. So we get this little bit of a difference. And we have this here, and it's kind of showing us the difference between these two. The range is still between -1 and 1. Those are our maximum minimum values. And our period is still 2 pi. But the peaks, where it's maxing out at 1 and negative, maximum is 1, minimum is -1, are at different points. And it's crossing 0 at different points. So in the figure of these here, note that with respect to the origin, where the cosine in this here, we have these properties. Now, like I just said, so we have our intercepts, where it intercepts the y-axis at 0, 0, 1, 0. So those are different. Now it also intersects the x-axis at pi and 2 pi. Well, that's where it's 0. For cosine, it intercepts the x-axis at pi over 2 and 3 pi over 2, because that's where cosine is 0. Maximum, maximum, minimum. And halfway between this one here, halfway between is 0. Now, if you notice, if we were to fold this onto itself, because if I take this point and put it here, well, it makes a circle. That's where we get the unit circle. Now we have this here. Now, we can go on and graph it, but I'm not too worried about this here, because we'd look at these points and would really want the intercept for this here, maximum, intercept, minimum, intercept, because it's going intercept max, intercept min, intercept in this wave, and we would get this darker function. Now if you notice, it's increased bigger, yes? The period is still between 0 and 2 pi. Because 2 sine of x, the period did not increase any faster. It just went up higher, yes? So having 2 out front doesn't change the period. It changed the, what we call amplitude, how high and low the peaks are. So when we look at this here, for any sine and cosine function, we get these two general equations. Y is equal to a sine of bx minus c plus d. And y is equal to a cosine of bx minus c plus d. I moved the d part to the end. So we have different components to this here. Now, the plus d, or d plus, should be something we're familiar with. This is a vertical translation. It's moving it up or down. So as I've kind of mentioned on and off throughout most of this chapter and before, I'm like this here, so the maximum minimum for sine and cosine is between -1 and 1 if we don't do anything to it. So on both of these here, if we added 3, well, the minimum used to be -1, but what are we doing to it? We're adding 3. So it would be, instead of -1, we add 3 to it, so it should be 2, because -1 plus 3 is 2. The minimum is now 2. The max was 1, but it's now at 4, because we're moving everything up 3. Or we could have gone down 3. So we can move it up or down. So that doesn't change anything. That's just like we've done with our quadratics or any other type of function. We can move it up or down, which means we can also move it left or we can have C, yes. Our C would be the horizontal translation.
Negative left or is it right?
So inside, if we just look at it, if it's x minus 3, well, the negative is a part of the equation. So the actual C value would be positive 3. Right. So an easier way to think about it is kind of the opposite of what we think. If it's negative, it moves to the right. If it's positive, it moves to the left. And when we say negative and positive, we're really just looking at what is the sign in front of the number, not what the actual value of C is. Now for this here, now, saying now a lot, we need to be careful, because when we talked about functions, we threw out horizontal translations, or not horizontal translations, horizontal stretches and shrinks. We kind of threw that out. We mentioned it briefly, but we didn't really talk about it. And that comes into play here, because really this horizontal translation is going to come in the form of C over B. Because for both of these here, I'm going to erase everything. What we're really looking at is a sine of B times x minus C over B. Because whatever that horizontal stretch or shrink is, has to be pulled out of the horizontal translation so that we can know what the actual translation is. And the same thing is true for cosine. So we have to take that stretch or shrink into account, or the change in period is what we're going to talk about here. Whatever the period is has to be pulled out of that horizontal stretch or horizontal translation. And that's it so far. So we good with this here? So our D value is our vertical translation. Our C is our horizontal translation. And we're going to call the B our period. We're not going to talk about it as a vertical or horizontal stretch or shrink. We're just going to talk about it as the period. And A is what we're going to call the amplitude. Now it's also our vertical stretch or shrink. Are the values going to increase faster or slower? Now the definition of amplitude is going to be the absolute value of A. So whatever that A value is, positive or negative, the amplitude is going to be the absolute value of it. So here, the graph y equals -3 cosine of x. So if we look at this here, the amplitude is going to be the absolute value of A, which would be -3. So the amplitude is 3. Now, cosine of x is a reflection of y equals cosine of 3x, so they have the same amplitude. One is just reflection over the x-axis. So they're similar, just the maximum and minimum have flipped. Yep. Questions on this here? Now, period, our B value. That's where this B value comes into play. Now, for sine and cosine, because the period we saw, it repeats itself every 2 pi units, is period is going to be equal to 2 pi over B, whatever that value is. And that will give us the period of the function, how many times it will repeat itself. is going to be 2 pi over b. Now this is mainly for sine, cosine, and really secant, cosecant will be the same thing, similar. It repeats itself every 2 pi. And we could have negative sine of x, but negative sine of x is equal to negative sine of x. So sine of negative x is equal to negative sine of x. And cosine of negative x is equal to cosine of x, or rewritten to rewrite the function. So much the inside, when we talked about function, was a reflection across the y-axis. But for the most part, it works itself out, because cosine is just going to end up being on itself. Sine is just the same as reflecting it over. So, now look at this here. Really, the amplitude is what we're going to look at first. Well, the value of A is, so the amplitude would be 1. Now, its period, well, this is the same as saying sine of 1/2 of x. So it'd be 2 pi over 1/2. So we can plug that in a calculator and see what we get. So you get 4 pi. So did the period get bigger or smaller? Mm-hmm. And let's go over 4. Let's go 2. Okay. So I pulled up this graph here. So I graphed the normal sine function first. Let's see here. No, I don't like that spacing. So it's going to be more spaced out. And we get something like this here, if we were to graph it. Because we can graph it using those 2 points. And that's it. I mean, we can do the same thing with cosine, using 2 pi. Not too bad. And now we can use the b minus c. Now, by solving this, because again, like I said, this b value, the period's going to change how we move to the left or to the right. So we have to factor it out to get what the true c is. And we can also, so this is our 1 point where it's moved, and then essentially we're adding 2 pi, whatever the interval is. So if it was moved, say 2/3, 2 pi over 3, we'll leave the pi on bottom, that's fine. That's what this value is. Well, we also have to talk about the movement to the other side. That's a little confusing. So this here, so if we said this was our original point, and we moved it over to the right, c over b. Well, the period, how much it repeats itself, right? I have to have it from there to where it repeats. That's why we have this interval. Because one of them is what it moved, the other is the period, how far. So it's talking about the shift. The left and right endpoints of one cycle can be determined by solving this here. Bx minus c is equal to bx minus c equals 2 pi and 0. So let's look at this here. So the amplitude. would be the absolute value of negative 3, which would be, so the amplitude is 3. Now getting the period isn't too bad because it's the b part of this here, yes? But let's go on and factor it out of these two here. So I'm going to factor 2 pi out of 2 pi x, which would leave us with 2 pi out of 4 pi would be plus 2. We shouldn't do anything for the period because our period is still going to be 2 pi. Sure. The period would be 1. Now our horizontal translation would be because it's positive inside the parentheses, it would be moving to the left 2. Questions on this here? So this here, solving the equation, we could get negative 2 and negative 1 would be the two endpoints. And this here would be our graph. Questions on this here? So now we can model this, and they do it a lot with waves. Now this example problem here, they're going to use water because water is the most common people think of as waves, but it's not only one. Sound. Yes. Well, depends because light is both a wave and a particle. It goes in both. So sound, light, anything that's harmonic in nature, up and down, that's going to repeat, can be used for this here. And it doesn't have to be the same, where the max and mins, these max and peaks, are the exact same. Because we can actually talk about, and we'll get to it eventually, where we could actually have a function and it should be the same on either side, but actually goes down and then goes back up. So we can actually have that. And we can describe it using these trig functions. And I mean, we could talk about this here, but I feel like we're good. That's this here. And that's it for 5.4. And it's really talking about those periods and amplitude in our movements. It's 18 minutes. So the other thing we're looking at is this here, graphs of other trig functions. Well, the first one is tangent. Now, if we notice, tangent was undefined whenever cosine was 0. Well, that means its graph's going to be a little bit different. And for tangent, well, tangent of negative x is equal to negative tangent of x, so it's odd here with respect to x, so that we end up getting such that x is equal to plus or minus pi over 2 as these undefined locations. Now it's going from negative pi over 2 to pi over 2. Well, this here is a distance of pi. So tangent doesn't have a period of pi, it has a period, or 2 pi, it has a period of pi. It repeats itself every pi units. So it has a period of pi. The domain is all real numbers except whenever we have some value of pi over 2, positive or negative. The range is infinite because as we see here, the graph is going up and down. Now the vertical asymptotes occur at x equals pi over 2 plus n pi, where n is an integer. And we can have the same thing similar to our sine and cosine. A tangent of bx minus c is similar to y equals a times sine of a bx minus c. In that we can identify the asymptotes. Well, we can use this information to find the asymptotes, but our amplitude, our a, we can factor b out and find kind of the period in our actual horizontal translation. So we would do the exact same with this, except instead of having 0 and 2 pi, we have instead equal to negative pi over 2 and pi over 2, because that's where it starts and finishes for these here. We can sketch it. So here, well, the amplitude is 1. But if we look at the period, well, this is the same as saying tangent of, now the period would be pi over b instead of 2 pi over b. So this here would be pi over, which would be 2 pi. So if we're going through actually graphing it, we would get some points, and then we can graph it. And that's it. So it's just expanded the overall period, the 2 pi instead of pi. Cotangent function is essentially the same thing, except now it's going down. Instead of increasing from right to, or left to right, it's now decreasing from right to left, or left to right. Now the period is pi, just like with tangent, except our asymptotes are now at n pi instead of pi over 2 n. So it shifted a little bit to the right. Asymptotes. And we have this here. Now this one here, if we were sketching it, the amplitude for it would be 2. Well, the absolute value of 2, which is going to be 2. Now the period, well, that would be pi over 1/3, which would be 3 pi. Get this here. So we get 3 pi. Now our n, so this starts at 0 and goes to pi. So we set it equal to 0 and pi and solve and find out one of the endpoints is at 0, the other endpoint's at 3 pi, because again, we said the period was 3 pi. Find our points, and then we can graph it. And as you notice, this one here is a little bit more stretched out than our original one, but that's it. Reciprocal functions, secant and cosecant. Now, secant and cosecant are going to have the same period as sine and cosine, but they're a little different because they're 1 over, right? So we have vertical asymptotes where cosine is equal to 0. That is at where x is equal to pi over 2 plus pi n. That repeated. And is similar as an integer. Similarly, 0 where it's at n pi. So this value is here. And if we sketched it, we actually get these here. Because the inverse, so it's going to be going up or down. So the ones that are shooting off, these here are our cosecant. These here are our secant. So they're going in the opposite direction. But it still has a period of 2 pi, because even though they're not connected, it's still taking, before I have a repeated value, a distance of 2 pi. So even though they're not connected, the period is still 2 pi. The only real difference in these here is that we have these vertical asymptotes. We have vertical asymptotes. And we have these peaks and mins. And if we looked at this here, we would know that the amplitude would be 2. Now there's a shift, what really I've been calling vertical shift. Sorry, not vertical shift, horizontal shift, horizontal translation. But that's not the correct verbiage. It just dawned on me. This is actually what they will call a phase shift of pi over 4 to the left. Questions on this here? By the equation, we get this. and we have our graph. And we could rewrite it as sine if we wanted to, but that's it. Dampen trig functions. That's what I was thinking of earlier. Because we can do x sine of x. And this actually changes what the function looks like. This is where we get this here. This x times sine of x actually gives us this increasing value. And it's going to oscillate. Sine of x is going to oscillate between y equals x and y equals negative x. It's going to switch between those two and stay within those range. We can use e, and we can get some points in our spots. And I'll do this here. So it's almost as we get a really loud noise, as it comes in and it'll get quieter. And that's really kind of our characteristics of these here. Secant, cosecant. That's it.